the only model our current computers can process. Are we actually studying ourselves anymore, or are we just projecting our own technology back onto our biology? Right now, the 3 pounds of wet, messy tissue inside your skull is doing something that a billion-dollar Silicon Valley supercomputer just cannot do.
Honestly, it's not even close.
Right. It isn't just processing the audio frequencies of my voice. It's instantly decoding the syntax, attaching emotional resonance, and, actually understanding the meaning behind the words.
Yeah.
You are generating an internal, subjective reality based on sound waves.
And humans have this almost desperate need to figure out how that wet machinery actually pulls off that trick. I mean, we look at ourselves, we look at our own consciousness, and we want a blueprint.
We want to take it apart.
Exactly. We want to take it apart and see how the gears turn.
Which is exactly why today's mission is so critical. We are undertaking an intensely detailed academic deconstruction of a text called 17 Neocortical Theories of Human Intelligence.
Yeah, and we aren't just skimming the surface here.
No, we are going to walk, step by step, through the philosophical and scientific logic of a major collision happening in science right now. The collision between actual biological neuroscience and the artificial intelligence paradigms of Silicon Valley. We're going to explore why viewing the human brain as just another computer might be a fundamental multi-billion-dollar scientific dead end.
Because when the tech industry looks at the brain, they often try to map their own software onto biology, and as we'll see, that leads to some pretty staggering assumptions about what intelligence actually is.
And this matters to you, because we aren't just talking about abstract academic debates.
Right.
We are talking about the very biological machinery you are using right this second to listen, to comprehend this deep dive, and to form your own thoughts.
Okay.
Well, let's unpack this. Let's start with the physical reality of the brain itself.
Right.
Before we get into the theoretical models of what the brain does, we have to understand the specific biological architecture those models are built on.
Yeah, and to do that, we have to go back to 1957, to a foundational discovery by an American neuroscientist named Vernon Mountcastle.
Mountcastle.
Yeah. Mountcastle was spending his days studying the neocortex.
The neocortex being that wrinkly outer layer of the brain, the part that essentially looks like a walnut.
That's the one. It is a dense layer of nerve fibers stretching over the cerebrum, and it is shockingly thin. We're talking about 2.5 millimeters thick.
Wow, just 2.5 millimeters.
Yeah, very thin. But Mountcastle wasn't just looking at the surface, He was probing the actual cellular structure. He was doing this pioneering work, inserting microelectrodes vertically into the somatic sensory cortex of cats and monkeys.
Okay, vertically.
Right. He wanted to see how the neurons fired when he applied different types of physical stimuli to the animal's skin.
So he's literally mapping out the physical wiring of sensation, like touch the skin, see which cell fires in the brain.
Yes. But here is the breakthrough. Mountcastle discovered that the neocortex isn't just a random, chaotic soup of cells. It's highly rigidly structured. As he pushed the electrode down vertically through that 2.5 millimeter layer, he found that all the neurons in that vertical column responded to the exact same stimulus.
Really?
Yeah, but if you move the electrode even a tiny fraction of a millimeter horizontally, he'd enter a totally different column of neurons that responded to a completely different stimulus.
Wait, so the brain is organized into distinct vertical pillars of cells, like individual silos.
Distinct vertical columns.
Yeah.
Yes. And here is the truly crucial part, the part that sets the stage for every theory we are going to discuss today.
Lay it on me.
Mountcastle proposed that every single one of these cortical columns appears to be fundamentally identical in its internal wiring to all the others.
Wait, identical?
Identical. Whether that column is sitting in the visual cortex processing site or the auditory cortex processing sound, the basic circuitry is the exact same.
So it's a massive factory floor of the exact same machines, just processing different raw materials depending on where they happen to be placed.
That is the physical reality. To give you a sense of the scale, modern estimates suggest there are about 500,000 of these columns in the human neocortex.
500,000?
Yeah. And inside each one of those 500,000 columns, there are roughly 60,000 neurons arranged in 6 distinct microlayers.
Okay, so we have 500,000 columns, 60,000 neurons each. It's a grid.
Yeah.
A massive, uniform, incredibly dense biological grid.
Yeah.
Now, I have to imagine that the moment you present a uniform grid to a computer scientist, they don't see biology anymore.
No, not at all.
They see a processor. They see architecture.
Which brings us perfectly to the first major theory in our text. And to understand this theory, you really have to understand the mindset of the person who created it, Jeff Hawkins.
Jeff Hawkins.
Yeah.
He is a fascinating figure to introduce here because he is not a traditional neurobiologist, right?
Right.
He is a Silicon Valley luminary, a computer scientist, an entrepreneur, famously the creator of the Palm Pilot. He's, pioneer of mobile computing.
And in 2004, Hawkins dips his toe into neuroscience and AI with a book called On Intelligence. He eventually founds a company called Numenta, which is dedicated to unlocking the secrets of intelligence by reverse engineering the neocortex.
Reverse engineering it, okay.
Right. So Hawkins looks at Mountcastle's identical uniform columns, and he proposes a purely hierarchical predictive model of intelligence.
Let's break down the mechanics of that. How does his model actually handle information, like day-to-day?
Well, Hawkins argues that the neocortex takes raw input from our senses and decodes it in hierarchical layers. Think of it as a physical cascade of data.
A cascade?
Yeah. The lowest layers of the neocortex, the columns closest to the raw sensory input, receive the primary data. Let's say you're looking at a coffee cup. The lowest layers process the most basic fundamental elements: a curved line, a straight edge, a patch of white color.
So they aren't seeing a cup yet. They're just seeing geometry and light.
Correct. They process that primitive data and pass it up the hierarchy to the next layer of columns. That higher layer combines the curves and edges into a more complex shape.
Okay, follow.
It then passes that shape up to the next layer, which might add the context of a handle. At every single step up the chain, the higher layer is tasked with making a prediction based on the data provided by the layer below it.
And this prediction propagates all the way up until the brain synthesizes a final conclusion, like, that's a coffee cup.
Exactly.
But the flow doesn't just go one way, right? The text notes that there's a feedback loop.
A vital feedback loop, yeah.
Yeah.
Because if the problem is easy, if you look at your own favorite coffee cup sitting on your own desk in broad daylight, the predictive loop terminates in the lower layers very quickly.
It doesn't need to go all the way to the top.
Right. The lower layers just say, we have a highly probable match based on our history. We don't need to bother the higher layers.
Mm-hmm.
But if the visual data is confusing, say it's pitch dark in the room and the cup is partially obscured by a book, the lower layers can't resolve it.
The problem is hard.
Exactly. So the data propagates up to more globally sensitive integrative layers of the cortex. Those higher layers synthesize a coherent prediction and then pass that predictive model back down the hierarchy to inform the lower layers of what they should be seeing.
It sounds like a corporate ladder.
How do you mean?
Think about a massive company. An easy problem, like a routine customer complaint, gets handled by the mailroom or the frontline customer service reps. They recognize the pattern, they have a script, they solve it. Done.
Right, right.
But a really tough problem, an unprecedented crisis, that has to be escalated. It goes from the mailroom to the manager to the VP, all the way up to the CEO's desk.
Yeah, that makes sense.
The CEO has a global view of the company, they synthesize a final strategy, and then that decision gets passed all the way back down the chain of command so the frontline workers know exactly how to execute.
That is a highly functional analogy. It really explains the latency in our own cognitive effort. I mean, why does it take you longer to recognize a strange object in the dark than a familiar one in the light?
Because it has to go to the CEO.
Yes, because the signal physically has to travel further up the cortical corporate ladder to reach a resolution and then travel back down. It maps perfectly onto the physical structure Mountcastle found, and it explains our empirical reaction times.
Okay, I see the appeal. It gives a really clean, logical flow to messy biology. But I have to push back on this.
Oh, go for it.
Isn't this just a bit too convenient?
Yeah.
You have a computer scientist, a guy whose entire career is built on designing hierarchical digital systems, and he looks at the squishy, profoundly mysterious human brain, and he just happens to see a perfectly optimized computational hierarchy.
Are you suggesting he's forcing a technological metaphor onto an organic system?
I'm asking if we are letting the tail wag the dog here. We know he builds computers. So he looks at the brain and says, look, it's a computer. Doesn't that seem like a dangerous bias?
I understand the skepticism, I really do. But you have to look at it from a biological energy conservation standpoint. The reason Hawkins' theory gains so much traction is because neat and tidy is exactly how evolution survives.
Yeah.
A massive, uniform, hierarchical grid is incredibly efficient. It minimizes the amount of unique genetic coding required to build a brain.
Because it's just the same column over and over.
Right. You don't need a separate genetic blueprint for the visual cortex and the auditory cortex. You just need one blueprint for a cortical column, and you copy-paste it 500,000 times. So the computational mindset isn't necessarily a bias. It might just be the recognition of nature's ultimate efficiency algorithm.
Okay, that makes sense. The physical architecture really is that uniform.
It is. And that uniformity, that mathematical precision, paved the way for another major tech giant to take Hawkins' hierarchy and push it to an extreme conclusion.
Oh, wow.
Yeah, because if the brain is a perfectly optimized computational hierarchy, then we should be able to quantify it. We should be able to count the processors.
Which opens the door for Ray Kurzweil.
Exactly.
We move forward to 2012, and Kurzweil publishes How to Create a Mind. He takes this hierarchical concept and mathematically supercharges it. He introduces what he calls the pattern recognition theory of mind.
Kurzweil is very explicit in the text that his theory builds directly on Mountcastle's neuroscience and Hawkins's hierarchical flow. But Kurzweil, being a pioneer in machine learning and data analysis, makes a very specific mathematical leap.
Right.
He hypothesizes that Mountcastle's cortical columns don't just process data, they contain discrete functional units that he terms pattern recognizers.
And he doesn't just theorize this abstractly, he puts a hard biological number on it, right? How does he calculate the math of human thought?
He starts with the neuron count. He hypothesizes that a single pattern recognizer requires roughly 100 neurons to function. That's the minimum hardware required to take an input, weigh its probability, and fire an output.
Just 100 neurons.
Yeah. Now, if we take the total number of neurons in the human neocortex, which is around 30 billion, and divide that by 100 neurons per recognizer, Kurzweil arrives at his magic number. He claims there are roughly 300 million pattern recognizers in the human brain.
300 million identical microprocessors firing away, passing patterns up and down the chain.
Exactly. And Kurzweil argues that these 300 million recognizers arranged in a hierarchy are centrally and solely responsible for the unique capabilities of human thinking. In fact, he uses this mathematical threshold to explain the evolutionary divide.
How so?
Well, he argues that animals without a neocortex, which is essentially all non-mammals, are fundamentally incapable of understanding hierarchies at all. They lack the physical hardware for stacked pattern recognition.
Here's where it gets really interesting. Because when you lay it out like that, 300 million processors doing basic math, it sounds plausible. But the sources we are deconstructing today point out a massive, almost fatal flaw in both Hawkins and Kurzweil's theories. Both of these men fall into the trap of believing that human intelligence is ultimately simple.
Yes. The text explicitly calls out the facile nature of these theories. I mean, when you take 300 million generic pattern recognizers and claim that this basic arithmetic is the secret to human thought, you are engaging in incredible mechanistic rigidity.
Yeah.
You are reducing the entirety of human consciousness to a biological spreadsheet.
Right. It feels like a fundamental mistake in categorization.
Yeah.
Reducing the richness of human consciousness. Art, grief, love, the invention of mathematics, the ability to write a symphony to mere arithmetic. It's too neat. It feels like we are mistaking the canvas for the painting.
That is the core of the debate right there. Knowing the physical structure of the brain, knowing that there are 500,000 columns and 30 billion neurons is one thing. We have the math.
Sure.
But this mathematical reduction begs a massive scientific question. What is that structure actually doing to create meaning?
We know what it is, but we don't know how it creates this subjective human experience.
Precisely. And this is where Gary Marcus enters the picture with one of the most blistering critiques of this entire Silicon Valley neuroscience movement.
Yeah, Gary Marcus does not hold back.
Not at all. Marcus is a cognitive scientist, and he looks at the models proposed by Hawkins and Kurzweil, and he dismisses them as hand-waving theories of AI based on vague insights about the brain.
Hand-waving. That is a brutal term in academia.
It really is.
He's essentially saying they were performing magic tricks, like, look at this hand over here with the math, while I hide the fact that I don't know how consciousness works in my other hand.
Marcus is zeroing in on a classic philosophical gap, the gap between syntax and semantics.
Right. Syntax versus semantics.
Exactly. Syntax is the structure. It is the grammar. In this case, syntax is the cortical columns, the 100 neuron pattern recognizers, the hierarchical flow of data. Semantics, on the other hand, is the meaning. It is the actual intelligence, the comprehension of reality.
Okay, I'm with you.
Marcus argues that just because we know the brain has a structured syntax, that doesn't mean we have magically mapped neural mechanisms to cognitive semantics.
To put it simply, knowing the alphabet doesn't mean you know how to write a novel.
That's a great way to say it. Knowing what the brain is made of doesn't tell us how the mind actually thinks. And Marcus doesn't just stop at calling it hand-waving. He brings up two incredibly specific counterexamples that absolutely destroy the idea that a generic hierarchy of pattern recognizers is the master key to human intelligence. Let's look at the first one, the rodent argument.
Ah, the rodent argument. This directly challenges the biological premise that hierarchical pattern recognition inevitably leads to higher intelligence. Marcus points out a basic fact of comparative anatomy. Rodents, like rats and mice, possess a neocortex.
Right, they are mammals.
Exactly. It is smaller, yes, but it is made of Mountcastle's uniform columns. Therefore, rodents possess the physical capacity for hierarchical pattern recognition.
And we know this. They can navigate complex mazes, they can learn intricate physical patterns and associate them with rewards. That is literally pattern recognition in action.
They do it quite well. But, as Marcus points out, rodents do not use language. They don't write poetry. They don't build space shuttles or philosophize about their own mortality.
No, they don't. If hierarchical pattern recognition is the definitive mechanism of intelligence, if it is the only software running on the hardware, why is there such a colossal cognitive gap between a rat and a human? Both possess the exact same biological machinery for pattern recognition.
And if Kurzweil's right, human intelligence is just a matter of having more recognizers.
Right. But scaling up pattern recognition doesn't explain the sudden emergence of abstract language or symbolic thought.
So it's not just a difference in volume, there has to be a difference in kind. The biological alternative isn't just more columns. There has to be something else going on. Maybe massive differences in white matter connectivity, or the immense expansion of the prefrontal cortex in humans that creates novel emotional and social processing networks that don't even exist in rats. It's not just a bigger spreadsheet. It's a fundamentally different operating system.
Exactly. Marcus is demanding that we look at the evolutionary biology, not just the raw processing power. Which brings us to his second point, which I find even more profound. The diner argument.
The diner argument. This is a great one. Let's put you, the listener, directly into this scenario.
Go for it.
Imagine you are on a cross-country road trip. You stop at a Greasy Spoon diner in a small town hundreds of miles from your home, a town you will never, ever visit again. You eat your meal, you pay your bill.
Now let's look at this moment through Kurzweil's model. From a purely mathematical, survival-based pattern recognition standpoint, leaving a tip for the waitress makes 0 sense.
0 cents at all.
Right. The transaction is complete. You have received the calories you need to survive. There is absolutely no future benefit to you to hand over extra resources. The pattern is closed.
But you leave 20% anyway. Why?
Exactly. Why?
Why do you voluntarily give up resources when there is no mathematical advantage? Is it guilt? Is it a complex internal moral framework? Is it empathy because you once worked in food service and you know how hard it is? A hierarchy of 300 million generic pattern recognizers utterly fails to explain human altruism.
It fails entirely because altruism, self-control, and moral dilemmas are not simply patterns to be recognized. They are internal conflicts to be resolved. Marcus asks, if we are just hierarchical pattern recognizers, why do humans constantly struggle with issues of self-control? Why do we procrastinate?
Right. A machine running a pattern doesn't procrastinate. A machine doesn't feel guilt over a diner tip.
No, it just runs the code.
It reminds me of looking at the blueprint of a house and claiming you understand the drama of the family living inside it.
Oh, that's a good analogy.
Right. Because, yes, you can see where the walls are, you can see the doors, you can trace the electrical wiring and the plumbing. That is the syntax. But the architecture alone, the blueprint, does not explain why the family argues at the dinner table. It doesn't explain the resentments, the inside jokes, or why they love each other. The blueprint is not the experience.
That is a phenomenal analogy. The blueprint is Mountcastle's columns. The family drama is the semantics of human consciousness. And these Silicon Valley theories are entirely obsessively focused on the blueprint. They are asserting that if you just draw a big enough blueprint, the family drama will spontaneously generate itself.
which is wild.
It is. Marcus is pointing out that hierarchical pattern recognition is an incredibly generic idea. It's actually a concept that has been around since the late 1950s in early computer science. Asserting that the human mind is just a legacy computer program tells us almost nothing about the unique, messy, beautiful reality of human nature.
But this brings up a huge question.
What's that?
If these theories are so generic, if they fail so spectacularly to explain basic, everyday human behaviors like leaving a tip or feeling empathy, why do brilliant tech luminaries keep proposing them? Why are these the guys writing the best-selling books and founding the neuro AI startups?
Because they are trapped in the mirror of their own technology. They're profoundly influenced by the tools they use every day. To understand the grip these theories have, we have to trace their origins. And that origin is the explosion of big data artificial intelligence.
We are looking at a technological mirror. The overlap between what these men do for a living and what they claim to see in the human brain is impossible to ignore.
It really is.
Let's look back at Kurzweil. Long before he was writing about the biology of the neocortex, what was his day job? He was working on machine learning for speech recognition. He actually worked on the foundational technology for the original Siri application for Apple.
Yes. And the underlying mathematical framework for that early speech recognition relied on something called hierarchical hidden Markov models. These are deep data analytic techniques that became foundational to the big data revolution.
Wait, I need a translation on that. What exactly is a hidden Markov model, and how does it function in this context?
Okay, think of it like a game of inference. Imagine you are locked in a windowless room. You have no idea what the weather is outside.
Okay, totally blind to the weather.
Right. But every day, your friend comes into the room. Some days they're carrying an umbrella, some days they're wearing sunglasses, some days a heavy coat. The hidden state is the actual weather outside. You can't see it. The observable state is what your friend is wearing.
Okay. I'm inferring the hidden state from the observable state.
Exactly. A Markov model is a mathematical system that uses the sequence of observable states to calculate the probability of the hidden states. If they wore sunglasses yesterday and carry an umbrella today, the model calculates the mathematical probability that it went from sunny to raining.
Okay, so it's guessing the hidden reality based on a sequence of visible clues. How does that translate to Siri understanding my voice?
Well, when you speak into your phone, the hidden state is the actual word you intended to say. The observable state is the messy, slurred acoustic waveform your phone's microphone picks up. The phone uses a hierarchy of these Markov models to guess.
A hierarchy again.
Yes. The lowest level guesses the phonetic sound. The next level up guesses the syllable. The highest level guesses the word, based on the probability of what words usually follow each other.
A hierarchy of prediction based on passing data up a chain. Sound familiar?
It is the exact architecture Jeff Hawkins proposed for the brain. And if we look at the broader AI landscape today, the ever-present deep learning neural networks that power facial recognition, predictive text, and generative AI, they're all arranged in these same hierarchies of data layers.
So modern deep learning takes massive data sets as input. The system churns through millions of examples, learns the mathematical patterns in that data, and induces a statistical model. And that model can then be decoded or applied to totally unseen data. It is highly effective for very specific tasks, like finding a tumor in an X-ray or translating a document from French to English.
It is effective for syntax. But here comes the creep into biology. The danger is that the tech industry started confusing their successful data models with actual biological reality.
They blurred the line.
Big time. We see this vividly with a researcher named Henry Markram. Markram introduces what is colloquially known as the Legos theory of cognition, proposed alongside his co-author, Rodrigo Perrin.
The Legos theory. Let's break this down. How do we get from brain columns to plastic children's toys?
Markram, once again, bases his architecture on the general findings of Mountcastle, the columnar hierarchical nature of the neocortex. But Markram focuses on neural assemblies, groups of connected neurons. The Legos theory suggests that acquiring memories, learning about the world, is quite literally like building a structure with Lego blocks.
The sources actually quote them directly on this. They write, each assembly is equivalent to a Lego block, holding some piece of elementary innate knowledge about how to process, perceive, and respond to the world.
What's fascinating here is how explicit, how literal the mechanical comparison has become. They are suggesting that your brain has preformed discrete blocks of innate knowledge, and when you learn something new, your brain simply snaps these blocks together in novel combinations.
Snapping them together.
Yeah. The synaptic connectivity rules govern how the blocks can connect, just like the little plastic studs on a Lego brick dictate how it can attach to another brick.
I have to stop and ask the obvious question.
Sure.
Are we just looking at a reflection? Are we only describing the brain as a deep learning network or a collection of modular software components, simply because deep learning and modular coding happen to be the trendy technologies of our specific decade?
It's a very valid concern.
I mean, think about history. In the 1700s, scientists said the brain was a system of hydraulic pumps because plumbing was cutting edge. In the 1800s, the brain was a clockwork mechanism. In the 1900s, it was a telephone switchboard. Are we just doing the exact same thing but with big data?
That is precisely the danger the sources are warning us about. We are anthropomorphizing our own technology and then reverse engineering it onto our biology. And the danger isn't just philosophical, it's a massive threat to actual scientific progress.
How so?
Because without existing organic biological theories to guide the research, these big data AI methods applied to neuroscience fall victim to specific computational failures. Researchers call these failures overfitting, saturation, and data-inductive blindness.
Let's unpack those terms. What does it mechanically mean when a brain theory suffers from overfitting?
Overfitting is a classic machine learning error. Imagine a student who is preparing for a math test. Instead of learning the actual underlying rules of algebra, the student simply memorizes the answers to every single question on the practice test.
Okay.
They are overfit to the training data. If the teacher gives them the exact practice test, they score 100%. But if the teacher changes even one number on the real test, the student fails completely because they didn't learn the concept, they just memorized the data.
So when applied to the brain, if you just collect mountains of data about how neurons fire, but you don't have a biological theory for why they fire, you just build a hyper-complex simulation of your own data. You map the practice test. You don't discover the rules of cognition.
Precisely. That is data-inductive blindness. You have so much data that you become blind to the underlying biology. You force the biological organism to become computational rather than letting the biology speak for itself.
And this isn't just an abstract academic debate happening in the pages of obscure journals. This specific computational bias, this total obsession with big data, directly hijacked one of the largest, most expensive scientific endeavors of the 21st century.
Yes, we absolutely have to talk about the Human Brain Project.
Let's talk about the fall of big science, because the real-world pushback against these data brain projects is staggering. When scientists realized that computer models were replacing biological hypotheses, they revolted. The source is, quote, Paul Matthews from a 2013 interview in the journal Nature, and he drops the hammer on this entire methodological approach.
Oh, he really does.
He states, I cannot think of major new conceptual advances that have come from such big science efforts in the past.
Matthews is pointing at a harsh historical truth. Massive data-centric computation dumping exabytes of data into a supercomputer has historically produced very poor and uninteresting scientific theories.
Right.
Theories that are suspiciously tied to whatever technology happens to be popular at the time. Yet, Henry Markram, the proponent of the Lego theory, managed to secure over €1 billion in funding to launch the Human Brain Project.
€1 billion.
Yes, pinning all his hopes on the idea that if we just simulate enough neurons on a supercomputer, consciousness will magically emerge from the data.
And that hubris led to an absolute mutiny. In July 2014, barely a year after the Human Brain Project was officially launched, over 500 scientists petitioned the European Commission. Over 500 working neuroscientists.
It's an incredible number.
That is not a minor academic disagreement over a footnote. That is a full-blown revolt. They demanded major systemic changes to the project because it prioritized computation and big data at the severe expense of actual creative biological research.
And the inciting incident that triggered that petition is deeply, darkly ironic. The revolt sparked when Henry Markram made the executive decision to shut down the Cognitive Architectures division of the Human Brain Project.
Wait, he shut down the division dedicated to exploring cognition, the exact division responsible for figuring out how the brain actually thinks.
Yes. Markram believed that exploring high-level cognitive theories was a waste of time. He believed that if they just perfected the low-level data simulation, if they just built enough syntax, the semantics would figure itself out.
That is crazy.
The neuroscientists recognize this as a fundamental violation of the scientific method. Because the scientific method has a core requirement, you must formulate and test specific hypotheses.
You can't just collect data without a question. It sounds like they convinced the European Union to build the world's largest, most expensive telescope.
Hmm.
But they were so obsessed with polishing the lenses and calibrating the data sensors, they completely forgot to hire any astronomers who actually knew what to look for in the sky. They built a massive machine and just assumed the machine would do the discovering for them.
That's spot on. Data collection without theory is a scientific dead end. More detailed computer simulations of a brain do not inevitably lead to a better understanding of the brain, just like a highly detailed video game simulation of a hurricane doesn't teach us how to stop real wind from blowing.
Right.
The result of this mutiny was severe. The scientific community pushed back so hard because they realized this wasn't neuroscience at all. It was a big data software engineering project masquerading as biological research. Markram was eventually forced to step down from the leadership.
And the Human Brain Project itself was completely retooled. The sources describe the aftermath. The project survived, but it was retooled as mere software engineering. It was stripped of all that grand AI mythology about simulating human consciousness, but in the process, it was rendered toothless for fundamental research. The dream of simulating the human mind computationally burned through €1 billion and collapsed.
Which brings us to a very harsh, sobering retrospective of the last decade of this AI mythology, because the promises made by these tech visionaries were not small. They promised the key to ourselves.
Let's jump to 2019. This was the 10-year anniversary of Henry Markram's notorious TED Talk. The TED Talk where he stood on stage and boldly proclaimed, without a shadow of a doubt, that the entire human brain would be mapped and functioning inside a supercomputer within a decade.
The ultimate statement of AI mythology.
And on that 10-year anniversary, when there was no conscious supercomputer to be found, major publications like Scientific American and The Atlantic published these really searching, highly critical accounts of what exactly went wrong.
And out of all those postmortems, there is one devastating quote from a scientist that summarizes the entire failure of the data-brain approach. Evaluating the billions of dollars spent and the petabytes of data collected, the scientist said, "We have brains in skulls, now we have them in computers. What have we learned?"
What have we learned? That is haunting. You spent the money. You built the massive server farms. You mapped the cortical columns. You simulated the neurons into a digital space. And the answer to what have we learned about human intelligence is nothing. We didn't learn why we leave a tip at a diner. We didn't learn how a rat differs from a poet. We just copied the syntax. But the semantics remain totally invisible to us.
To contextualize why this failure was so profound, the sources include a comparison from the Nobel laureate and Columbia University neuroscientist Erik. He compares the massive efforts to map the brain like U.S. Brain Initiative to the Human Genome Project.
Those seem like similar massive biological endeavors. What is the difference?
Kendall points out that with the Human Genome Project, the scientific community knew exactly what the endpoint was. The goal was concrete and definable. Map the sequence of the human genome. Once the sequence is mapped, the project is a success.
Right, it's finite.
But with the brain, we don't even know what the goal is. As Kendall puts it, what does it actually mean to understand the human mind? If we map every single synapse, do we understand it? No. When will we be satisfied? It is a fundamentally different and infinitely more ambiguous ambition than simply mapping a genetic sequence.
Because mapping the structure of the mind doesn't explain the subjective experience of the mind. So what does this all mean? We look at Hawkins's hierarchical ladders, Kurzweil's 300 million pattern recognizers, Markram's Legos, the mutiny of 500 scientists, and the billion-dollar failures of big science. Where does this intense deconstruction leave us in our understanding of ourselves?
It leaves us with a stark, undeniable philosophical conclusion drawn directly from the sources. It is fundamentally bad science to operate on the blind faith that big data and machine learning algorithms will magically provide answers about human insight.
Because human insight, human creativity, and human logic are the exact things that built those machine learning systems in the first place. You can't use the tool to explain the hand that wields it.
Exactly. The data brain enthusiasts assume that if they just gather enough data, the deepest mysteries of human intelligence would organically reveal themselves out of the noise. But intelligence is not just a byproduct of data volume. Relying on sheer computation as a substitute for creative, hypothesis-driven biological research creates a sterile environment, an environment devoid of real future discovery. We must demand wider-ranging, disparate research agendas if we truly want to understand the organ inside our skulls.
So, to synthesize this entire journey, yes, The neocortex is a beautiful, highly structured 2.5 millimeter columnar architecture. Vernon Mountcastle proved that in 1957.
Hmm.
And yes, that biological grid is incredibly inspiring to tech visionaries. It looks like code. It looks like a silicon chip.
It really does.
But the essence of human thought, our morality, our empathy, our ability to invent language, our bizarre compulsion to leave a tip for a stranger in a diner we will never see again, cannot be retrofitted into the latest Silicon Valley software paradigm. We are not just a collection of 300 million pattern recognizers. We are not biological Legos waiting to be snapped together.
No, the structure is not the system. The blueprint is not the family.
Which leaves you listening right now with a final thought to mull over as you go about your day. If the brain isn't just a biological computer running big data algorithms, and if our current technological metaphors are actually blinding us to the complex truth of how we think, what if the real secret to human intelligence lies in studying exactly what computers cannot do? Maybe our truest intelligence isn't found in our ability to recognize a pattern, but in our messy, illogical, profoundly human ability to break one. Thank you for joining us on this deep dive into the neocortex.